So in today's lecture, we will discuss geometrical interpretation of derivative. In fact, it is also a part of the application. Now to start with, the first thing is that geometrically we can interpret the derivative, means dy dx, and it has got a tremendous applications in various fields of mathematics as well as in other sciences. Now first we look at the definition, because this is very much required to understand the geometrical interpretation. You know that we can define the derivative of a function y is equal to fx at a point x is equal to c by this formula. By this formula means by this limiting value. Limit h tends to 0 f of c plus h minus fc by h. That is this. And this limiting value we will require when we will explain the geometrical interpretation or geometrical significance. And to do that, we look at this picture. So here we have the graph of the function, this APB or APQB, you can call it. This is the graph of the function y is equal to fx. And we have taken from this origin O, we have taken these two distances. For the point P, you can see that this OM, that is this OM distance is, we have assumed this is equal to C, this length is C, OM, and this length ON corresponding to the point Q, this ON is C plus H, means from M to N the distance is H. And consequently, if this OM is C, then this PM, this length PM will be what? F of C, and the length Qn, because this ON is C plus H, so this Qn is f of C plus H. So if we want to find this length QR, this will be what? This Qn minus this PM. So it is f of C plus H minus f of C. So it is f of C plus H minus fc. And then if you consider QR by PR, this ratio, QR, this length divided by PR, then that will be what? That will be your f of C plus H, this length, divided by, this is simply H because this is C plus H and this is C. So this difference is H. So FC plus H minus FC by H, this ratio is actually your QR by PR. And if we consider, if we take this angle as theta, this angle means the angle which this chord PQ, this extended chord PQ of the curve makes with the positive x-axis. So if this angle is theta, then this QR by PR is actually, if this angle is theta, then this angle is also theta. This angle QPR is also theta. And then QR by PR will be equal to tan theta. So this is the first deduction that we require to understand the geometrical interpretation. So what we got? We got this QR by PR, that is same as f of C plus H minus fc by H corresponding to the function y is equal to fx is equal to tan theta. Now our intention is to make such an arrangement that the point Q coincides with the point P, means the point Q slides down to the point P. So how that can be made? Now you see that this Q and the P, these 2 points are actually differentiated, means they are separated by the distance which corresponds to this distance PR. Just you see that if this point Q comes down to the point P, then what will happen? This PR should not be there, this PR will vanish. So actually we are taking, in the next slide you see that this PR, now if this PR vanishes, this PR is same as this Mn. And what is this Mn? We have just seen that this Mn is actually, this length Mn is H. So this PR will vanish when this Mn will vanish, means it will be very small, and that very small means we are making this length of PR 0, tends to 0. So that is what we are making, that H tends to 0 because the length of PR is H. So we are considering this limit fc plus H minus fc by H. We have just seen that this fc plus H minus fc by H, this is equal to QR by PR. So this QR by PR means FC plus H minus FC by H. We are taking the limit of that as H tends to 0 means when PR tends to 0, and that is equivalent to the point Q tends to the point P. And the point Q tends to the point P means what? The point Q tends to the point P means, you see that when this Q comes to the point P, then this chord, actually this PQ chord, PQS, QPS chord will be identical with the tangent PT. Because in that case, what will happen? This will come down to here. So this line will become this line. This line will become this line. So now this line becomes this line means what? The angle theta tends to the angle psi. The angle theta tends to the angle psi, and that is what we have written here. You see that Q tends to P means theta tends to psi. So what this limit becomes? Here you see that QR by PR, that is FC plus H minus FC by H, was tan theta. So here in the limit, when you are considering the limit as H tends to 0 means Q tends to P means theta tends to psi, means that this theta, this line becomes identical with this line, means this chord becomes identical with this tangent at this point. So theta tends to psi. So limit tan theta, theta tends to psi, that becomes tan psi. So what we get? F dash c. Now this thing, that is this limit H tends to 0, fc plus H minus fc by H. This is, we know, this is the derivative by definition. So this is your dy dx at x is equal to c or f dash c. So we see that this derivative ultimately becomes equal to tan of psi. So what is this psi? This psi is actually the angle which we have just seen here. The psi is the angle which the tangent at the point P makes with the positive direction of the x-axis. This is angle psi. So what we get? We get that derivative is actually dy dx at x equal to c is actually equal to the trigonometrical tangent of the angle psi which the geometrical tangent makes with the positive x-axis. So this thing we call the geometrical significance of derivative, and this has got some tremendous applications. Now I'm just showing a very small application. So by using this, we can find the slope of the tangent of a curve, or actually we can find whether the tangent becomes parallel to x-axis or perpendicular to x-axis, and so on. Now what we have seen here from the above discussion, you see that this one, from this one, that the derivative dy dx can be identified with tan psi, where psi is what? Psi is the angle with the tangent which the tangent at the point P makes with the positive x-axis. So from these two we can say that dy dx at the point P, means at the point C in our case, is the slope of the tangent to the curve y is equal to fx at P, and that we write it as tan of psi, because it is the psi is the angle which the tangent at P makes with the positive direction of x-axis. Now if the tangent is parallel to x-axis, tangent at the point P is parallel to x-axis means what? This angle psi will become 0. So that will mean that dy dx at the point P will be equal to 0. So this from our discussion, that is the geometrical significance discussion, what we see, geometrical interpretation, that from here we can find when the tangent becomes parallel to x-axis by using the derivative. And tangent, when the tangent becomes parallel to x-axis, this helps us in finding a various other things. In a subsequent lecture, we will discuss about maxima minima of a function, and there also we required this concept, that is the concept when if the point where the tangent to a curve becomes parallel to x-axis. Now this thing, that is by using this geometrical interpretation, we can find the slope of the tangent. We just see one or two examples on that. Now the first example, you see, first problem, find the slope of the tangent to the curve y is equal to x square minus 2x plus 3 at the point 1, 2, and find the points on the curve, the tangent at which are parallel to x-axis. So here we just use this concept, this idea. So what we do here? Here you see that the curve is y is equal to x square minus 2x plus 3. So from this curve we can find out dy dx by differentiating with respect to x. So that gives you 2x minus 2. Now 2x minus 2, so if you find the value of dy dx at the point 1, 2, we see just by putting 1, 2 in this expression, we are getting that the value of the derivative dy dx at the point 1, 2 is 0. So that means what? That means that dy dx at this point is 0 means what? The tangent at this point, 1, 2 point, is parallel to x-axis, because we have just seen that if the dy dx at the point P is 0, that means psi is 0 and means the tangent is parallel to x-axis. Now similarly you can see another problem, find the point on the curve y is equal to 7x minus 3x squared, where the inclination of the tangent with x-axis is 45 degree. Now here for this situation, what we can do, just see that first of all you find out 45 degrees. So the tangent inclination of the tangent to the x-axis with the x-axis is 45 degree, means our dy dx at the point P, we have to find out the point P. So dy dx at the point P will be tan of 45. So that means 1. So dy dx at the point P will be 1. Since it is given that the tangent at the point, you have to find the point where the tangent at the point is inclined at an angle of 45 degree with the x-axis. So our psi is 45 degree. Now we find out dy dx for this curve. Y is equal to 7x minus 3x square. So what do we get? Dy dx is 7 minus 6x. And then we find out that, so what will happen? So this dy dx at the point P, we can find out because we have taken the point P as x1 y1. So what is dy dx at the point P? Just by putting x1 y1 in this dy dx, we get it is 7 minus 6x1. So this 7 minus 6x1 should be equal to 1 because it is given that the tangent makes an angle 45 degree here. So what we are getting, 7 minus 6x1 is 1. That gives us x1 as 1, value of x1 as 1. And then if you know x1, simply you can find y1 because the point P x1 y1 is on the curve y is equal to 7x minus 3x squared. So by putting the value of x1 in this curve, you can get y1, and that y1 is 4. So we are getting that the required point where the tangent to the curve is inclined at an angle of 45 degree with the x-axis is 1, 4. So this is how we can use the geometrical interpretation of derivative to find out slope of tangent. In a similar process, you can find out the slope of the normal also. And not only this, as I have just mentioned, these are used, in geometrical interpretation are very extensively used in the concept of finding maximum minima of a curve, which we will discuss in a subsequent lecture. Thank you.